Hey guys, in this video I'm going to talk to you about the equations of motion, how they are derived, and in what situations they can be useful. First of all, what are they about? The equations of motion describes the behavior of a system in terms of its motion as a function of time. In other words, we can use these equations to predict the behavior of moving bodies or projectiles as it evolves through time. There are a set of 5 equations which provide a good approximation given its simplicity. You'll see what I'm talking about when we get to the worked examples. In order to use these equations, we need to make a number of assumptions. These include that bodies move at a constant acceleration, that there are no external forces such as friction involved, that bodies move linearly in one dimension, and that they travel at non-relativistic speeds or at speeds close to the speed of light. These equations are normally dubbed the Suvat equations. That is because Suvat is an acronym for the variables which are used in these equations, where S is the displacement, U is the initial velocity, V is the final velocity, A is the acceleration, and T is the time. It's always useful to begin by looking at the velocity-time relationship. We can create a chart for a moving body where we map the velocity against the time. In this case, what you see is a body moving at a velocity which increases at a constant rate. In this next case, what we have is the moving body whose velocity increases, again at a constant rate, but at a rate which is lower to the previous example. And then the velocity becomes constant, and then the velocity decreases again at a constant rate. However, in real life situations, what you have is that the velocity is always increasing or decreasing at varying rates. But for the purpose of this exercise, we'll take our first example and see how this sort of chart can be useful to us. If we take the gradient of this line, in other words, the change in velocity over the change in time, what this tells us is for that measured period, the acceleration of that moving body. Also, if we measure the area under the line, what this tells us is the distance traveled by that moving body for that period that is measured. If we look at the acceleration, acceleration is the rate of change of velocity. As we saw before, A is equal to delta V over delta T, where delta denotes the change. We can write delta V as the final velocity minus the initial velocity, or using our Suvat variables, V minus U over T. We can rearrange this equation to say that V is equal to U plus AT. And this is our first equation of motion, which I will call equation 1. Next, let's look at velocity. Velocity is the rate of change of displacement. In other words, V is equal to S over T. However, for moving bodies, velocity is not really always constant. So we usually measure average velocity, in other words, a half of U plus V. If we substitute average velocity for V in our first equation, as such, we can rewrite this to say that S is equal to a half U plus V times T. Our second equation of motion, equation 2. Now we can simply derive the 3 remaining equations of motion through substitution of our equations 1 and equations 2. Let's start off by substituting equation 1 into equation 2 for V, where V is equal to U plus AT. And what we get is S is equal to UT plus a half AT squared. our third equation of motion, which I will call equation 3. Again, starting off with equation 1 and equation 2, we substitute equation 1 into equation 2 for u, where u is equal to v minus at. And what we get is s is equal to vt minus a half at squared, which I will call equation 4. And then finally, what we do is we substitute equation 1 into equation 2 for t, where t is equal to v minus u over a. And we get the relationship of v squared is equal to u squared plus 2as. Our final equation of motion, equation 5. So to summarize, these are our 5 equations of motion. And what you see is that each equation makes use of 4 of the 5 suvat variables, and each one having a different combination of the 4. So I may ask, why do we need 5 equations and how are they useful? Well, if we knew 3 of the 4 variables for each equation, then we can use that equation to find out the 4th. It's probably better looking at an example. Let's say a rocket lifts off with an acceleration of 20 meters per second squared. How fast will it be traveling after 20 seconds? It's always best to approach this by listing the suvat variable and using the question to fill in the values. So we don't know what the displacement is. The rocket lifts off with 0 initial velocity. You want to find out what its speed is after 20 seconds. Its acceleration is 20 meters per second squared, and we are measuring what the speed is after 20 seconds. So looking at this, we can discard s, or displacement, and use an equation of motion which utilizes u, v, a, and t. And from before, we can use equation 1. Simply substituting in the values, what we get is the velocity is 400 meters per second after 20 seconds. Let's look at another example. A train is traveling at 20 meters per second and accelerates at 0.5 meters per second squared for 30 seconds. How far will it travel in this time? Again, similarly, listing our suvat variables, and we insert the values we know from the question. In this case, we want to know the displacement, or s, and we can discard v. So an equation which has s, u, a, and t, that will be equation 3. And again, inserting all our values that we know, we find that the displacement or distance is 825 meters. One more example. Let's say a ball is dropped from a height of 20 meters. And what speed does it hit the ground? You might think this doesn't give you a lot of information, but what we can say is the distance is 20 meters. It is dropped from a height of it is dropped from an initial velocity of 0. We want to find out what the velocity is, and the acceleration will be gravity, which is 9.8 meters per second squared. So we can discard t and use the 5th equation of motion, and inserting the values, what you find is that it will hit the ground at a speed of 19.8 meters per second. So in conclusion, the equations of motion are only truly accurate for motions of bodies when we consider the various assumptions. Despite this, it's a useful tool for approximating real-life situations. We can further extend the idea by introducing calculus to account for changing acceleration. However, that's for another time. Thanks for watching.